Cool. The title of my presentation and the work is Language Agnostic Text Processing for Information Extraction. So just now from Lekai, we have actually heard about the importance of features in music, right? Similarly, any domain that we talk about, feature extraction or featurization is a very, very important and critical component. Now, in this work, what we are trying to do is we are trying to again play with the featureizer and try out multiple combinations and permutations of featureizer and try to build a pipeline which is language agnostic in nature. It is not depend on any language and it will work on multiple languages. So that's the point. So the flow of the presentation is organized as I will have a little bit of an intro to multilingual natural language processing or NLP. Then I'll put forward a study case of a conversational assistant, which we have used in this particular research to aid our study. Then I will talk about the development of the language agnostic pipeline, the considerations that went into it, the combinations that we have tried out, etc., followed by experimental evaluation showing whether this pipeline actually works or not, and I'll conclude my talk. So introduction to multilingual NLP. NLP being natural language processing, as we all know. So basically, multilingual NLP, what it tries to do is make a computer understand multiple languages. So making a computer understand one language itself is difficult. So you can imagine the multifold challenges that will go into multilingual NLP. It will be always advantageous if we can build a truly language agnostic system. But what I mean by language agnostic system is, for example, take a text categorization system, which is basically takes in news articles in multiple languages and categorizes or classifies these articles into political news, entertainment news, sports news, etc. By language agnostic, this particular text categorization model should be okay to take in news articles in English, Hindi, Malayalam, multiple Indian languages, or any language for that matter, and still be able to classify them. So multilingual NLP should realize various NLP tasks in multiple languages, but while doing so, it should not perform any language specific steps. At least when we use the system, there should not be any language specific steps for an end user to perform. And this system should be okay to port from one language to another language without any additional processing, at least in the usage stage. So that is multilingual NLP. Why multilingual NLP? So this is a sort of a very self-explanatory question in itself, right? We all live in highly rich multilingual societies. India has 27 scheduled languages in usage. And there are Europe being a very rich multilingual society. The Americas is a very multilingual society. And traditional natural language processing systems usually use language-specific models and strategies. So in order to realize multilingual NLP, we need to build language-specific models in each language under consideration. And then we should be able to plug and play with these multiple models to realize multilingual NLP. But if we actually have a language agnostic system or a multilingual NLP system, then we may not require huge amount of language specific resources to build that system or to operate that system. Applications of such a system is multifold, as I already mentioned. Think about an example of a conversational assistant which can understand queries of a user in multiple languages and reply back. For example, if there is a customer care of an ISP provider, we may actually can complain about I'm not getting internet properly in English or Malayalam. If there is a conversational assistant for a banking application, we can actually inquire about car loan interest in English or Malayalam, and the assistant should equally understand these queries equally well and respond intelligently. Another application that I can quickly think of is automatic management of archives, right? The amount of print or virtual text out there is huge. There are a lot of media houses, there are a lot of publication houses, there are a lot of research publication houses in our case, right? So if there is an automatic system that can categorize or do some sort of information extraction from these articles in multiple languages and categorizes them and organizes them efficiently for user retrieval and usage, that would be a huge advantage. Another interesting application that I would like to point out is code switching. Code switching is a scenario when within a sentence multiple language occurs, and this is a very common situation with people who speaks multiple languages, right? We sort of plug and play, and in a society like India, we always mix English with our mother tongue or another regional language. So this is a very interesting scenario, and this scenario is very common in social media posts, movie reviews, etc., etc. So if we have a multilingual NLP or a truly language agnostic NLP system for performing any of the NLP tasks, it will be hugely beneficial for social media analysis, movie reviews analysis, etc. So these are the reasons why we should go for multilingual NLP rather than multiple language specific NLP models. Now, the obvious question, right? How to perform multilingual NLP? So traditionally, as I already mentioned, we researchers or users would obviously go for language specific model. So if we have 5 languages under consideration for a particular application, we build 5 different models, language models for these languages. And then there will be a language identification system in the front end, which will route the inputs in a particular language to the corresponding language model. But again, as we can imagine, this is like it's a computationally expensive, not practical solutions, because we have to build language models in each language. Another most common solution was like, build one language model, put all your resources, all your data into it, and build one language model. And when another language comes for a particular NLP task, translate that to this particular language model's language, perform the NLP operation, and translate it back to the language of your interest. This approach has its own problems because the transliteration strategies are again not error-free. So when we put another module for translation or transliteration, it will just add to the error of the already existing NLP pipeline, which will result in error accumulation. Another strategy is data augmentation. This is particularly used for code switching scenarios to generate code switched text and process it using existing NLP models. And we have observed that this is not a very effective strategy, because when you are doing data augmentation, we'll have one strategy in our mind, and when we put it for actual applications in real world scenarios, there will be a huge domain mismatch, and the accuracy kind of deteriorates. Another more important and popular strategy is find pre-trained resources, then get a little bit of data in the target language and fine-tune the pre-trained resource. By pre-trained resource, I specifically mean language models, pre-trained language models. This strategy will also be useful if you can find a pre-trained language in the language model in the particular language of your interest. So as a natural extension to this, people coined this idea of transfer learning, which we all are familiar with. I'm quite sure I'll just brush through it. So you can build a language model in one particular language for a particular task, and then port that language model's knowledge to a different target language. So the source language and target language are not same in this case. But for this strategy to work, again, the models bank on some sort of syntactic or semantic similarities between the source and target language. Another sort of transfer learning is domain transfer, where the model is built for one particular domain of data, like medical text domain, and we have to in English, and both the languages are in English. So the model is built for a medical domain text data, and now you have to use the same model for entertainment domain text data. So then we have to fine tune for a domain transfer. Task transfer is another, it is completely cross-lingual and cross task, which is outside the scope of this talk. We'll just skip through it. So in order to realize the cross-lingual or domain transfer, language representational models are the way to go. And language representation models took a huge dive towards the 2016 and onwards by the advent of Google's BERT. BERT is a transformer architecture with a positional encoding in it. It basically, for the language representation, we are only using the encoder part of it. So the encoder will provide encoded representations or embeddings. How do they train BERT is they pulled a large amount of text data and it strategically masked out 15% of words at any given epoch. So by doing this strategy, they try to mimic the bidirectionality of the learning. So each word or a token, its representation is learned by the neighbors towards the left-hand side as well as the right-hand side. And they learned by predicting the next word. So the next word prediction is the objective of learning. Now, a natural extension of BERT, which is largely trained using large data of English, trained for specifically for English language, people started copying it or mimicking it for other languages. And as a natural extension, Google released its multilingual BERT, which was trained by pulling in data from 100 plus languages. There are other strategies like cross-lingual pre-training coined by Facebook, and now there are multiple massively multilingual models exist like MBERT and XLMR. So these models or encoders provide these embedding representations, which essentially captures the meaning and context of a word by inspecting its occurrence inside the training data. So the idea behind or why is it working, why is it effective is that even though there are multiple languages under our consideration, the words with similar meanings or same meanings in multiple languages will have their embedding vectors which are pretty close to each other. So it is not just learning the probabilistic distribution of words in the data or anything like that, but it is actually learning the meaning of that word. Now, just to summarize, massively multilingual models like MBERT provides us with embedding representations for text from multiple languages. How does it represent these text or tokens / words of the data is by training on multilingual data using completely unsupervised learning. And it captures the meaning and context of the words so that the embedding, the resultant embedding is a faithful representation of the text. And words with similar meaning from multiple languages will be represented by closer vectors. As an application, we can use these embedding representations as, of course, as a representation of words or sentences at any given level. And we can take these vectors and use it for any downstream tasks. But I have to stress this point, even though massively multilingual models like MBERT or XLMR are trained on huge data, these data are obtained from sources like Wikipedia and books. So it actually lacks context and domain knowledge when we actually put to use for specific tasks or specific use cases. So in that case, it usually requires a fine-tuning with a limited domain-specific or language-specific data for a particular application. In order to aid the study of or this research, we actually chose the use case of a conversational assistant as a case study. And the problem statement that we tried to solve was information extraction from customer queries received by this conversational assistant. So they are short text messages or with the length of 1 or 2 sentences, not a huge text like an article. And we tried this to make information extraction as a part of natural language understanding happen for multiple Indian languages, by which I mean English is, of course, we have taken it, and Hindi and Malayalam. And we took two scenarios of code mixing between English and Hindi. Let's move to our case study. So I'll quickly go through this. We have actually taken the case of a conversational sales assistant. So this sales assistant, conversational assistant, is supposed to receive customer queries about an intended purchase, and it is expected to answer these queries. And the queries expected are English, Hindi, and Malayalam, and code switching of English and Hindi. We realized or built this conversational sales assistant using the Rasa Framework. Rasa Framework is an open source platform for building chat-based, that is text-based or voice-based conversational assistant. So this framework lets us create process pipelines for natural language understanding and responding to the queries. So Rasa has an NLU which uses a classifier called Dyad for intent classification, intent recognition, and entity extraction. And Rasa Core manages the dialogue policies so that it can decide what to respond to each of the users or the customer queries. It also lets us integrate with external libraries and pipelines like Spacey, Hugging Face, etc. It's a pretty versatile and an open source platform. It has a pro version also, which we did not use. Now let me explain the query setup. We call this conversational assistant as a limited query setup assistant. It expects customer queries in 4 intents and containing 4 entities. So the customer queries should belong to greet, goodbye, product details, or product price. And greet and goodbye are simple intents because it's like hello, hi, namaste, or bye, thanks, etc. Whereas the product details and product price are a more complex sort of intents because the query comes under these classes, or these intents are little bit complex with maybe 1 or 2 sentences and mentions of multiple entities. And entities, for that matter, whatever the entities we are interested in this limited query setup are 4 entities: name and location or city of the customer. Because if you're talking about a conversational assistant for a dealership or a manufacturer, they would like to contact that customer for further follow-up. And then the other 2 entities are product class and product name, which is if it is a line of cars that the customer is interested in, it is product class, and a specific car within that line is product name. Out of which these entities, name and location, are unrestricted entities, which means it can take any value in the world, right? We are like millions of people in the world, and each one of us have a different name. And same goes to the cities in the world. On the other hand, so we call it as unrestricted entities. On the other hand, product class and a name, particularly for a specific use case, are restricted entities. If we are talking about an electrical appliances manufacturer, that particular manufacturer will have a specific set of ranges of products, and within each range, there will be a limited number of actual products. So these are restricted entities. So this is our query setup. And in our problem statement is do information extraction from these customer queries. So the natural language understanding or information extraction contains 2 steps here: intent classification and entity extraction. So if you look at the example, like a product details, I would like to know about different options in washing machines is a customer query. Then my system or NLU has to understand the intent of the customer as product details, and the entity mentioned is washing machine. So this is the task, and we have to do this task in multiple languages and code switching scenario. And for an experimental purposes, we actually try to match between a language specific strategy and a language agnostic strategy. So to summarize, we are trying to perform natural language understanding of customer queries, and customer queries are usually short text messages. We have to realize the intent of a customer, what is that person trying to find out, and also the entities mentioned in that customer message, which is basically his or her name, location, or the product that person is interested in. Now, understanding these details like intent and entities will help the conversational assistant to generate intelligent responses and give it back to the customer. So the problem statement is information extraction from customer queries, and we have to perform a closed set intent classification, that is 4 classes, and a closed set entity extraction, which is also 4 classes. Now I'll talk about development of a language agnostic pipeline. How do we do it? The pipeline for natural language understanding by language agnostic, what we mean is that this pipeline should work for multiple languages. So usually there are steps like text pre-processing, featurization, classification, etc. in this pipeline, and each component, each of these process components should be language agnostic. And we have to perform intent classification and entity extraction as a part of NLU, natural language understanding. And what we try to use is we try to utilize commonalities between languages. And of course, we will try to use massively multilingual models to make it happen. So let's talk about each component one by one. So pre-processing usually have basic sanity checks for the data, punctuations removal, etc. And another important step is tokenization. So most of the languages that are under our consideration are white space separated text. We put a space between words. So white space tokenizer is a common and obvious choice to go at this point. And white space tokenizer, as I was saying, is basically language agnostic. It is just looking for white space and separate your sentence into tokens. So we have used Rasa's white space tokenizer, or one can use Spaces tokenizer as well in the pipeline. So we have included sanity checks, punctuation removal, and white space tokenizer in our NLU pipeline. Now, the most important component, right? Featureization. Featureization represents basically text by feature vectors or embedding vectors. Here we did some rigorous experimentation. So we started with sparse features first. Sparse features, we try to include 3 of them actually. First one is syntax and semantic of a language, or lexical syntactic featureizer, which can actually capture very simple information like whether a token is existing in the appearing in the beginning of a or ending of a sentence, whether a token is an all-digit token, etc., and more complex information like part of speech of that token. Here, I would like to point out that part of speech is again language specific. It is not language agnostic, but for the time being, we are trying to ignore that factor because it will just contribute to a small piece of one of the features. So we are just trying to ignore the language specific nature of that part of speech tag. And whenever the part of speech is applicable, like for a language like English, a meaningful vector will come, embedding will come from there. If not, it will be all zeros, which will be taken care of anyway in the rest of the pipeline. The second featureizer that we are looking for is regex featureizer. This is particularly important for entity extraction and for entities like product, class, and name. Try to imagine a manufacturer, like a car manufacturer or an electrical appliance manufacturer. They will have a specific nomenclature strategy to name their products. So, for example, Mercedes XYZ. BMW XYZ, right? So the XYZ will be a specific nomenclature, and if we try to, and they will have specific entity patterns. So by using regex featureizer, we can actually capture those entity patterns, which will contribute to the accuracy of entity extraction. Then the most important featureizer is n-gram featureizer in the sparse, which is also a sparse featureizer, which is basically a probabilistic representation. It is just counting the words, number of occurrences of a word in your training data, and sequence of words occurrences. So it's basically by counting or by finding out the probabilities, it is trying to capture the probability distribution of words and sequence of words in a particular language. So this will also contribute to sparse featureizer. And dense featureizer is nothing but our language representation models, encoder representations. Here we are trying to use multilingual BERT, which Rasa allows us to do by integrating with Hugging Face. And finally, we put sparse and dense featureizers together as a linear combination and make composite featureizer. So all in all, The next block or process component in our pipeline is classifier. We are just using Rasa's diet classifier, no investigation done here. Rasa's diet classifier is a multitask transformer model which performs intent and entity classification together. And all in all, finally, we came up with this pipeline, which is completely language agnostic in nature. Whitespace tokenizer is language agnostic. Our featureizers are language agnostic, except for the part of speech tag. And classifier is anyway language agnostic because it works on vectors rather than languages. So we have come up with a developed language agnostic pipeline. Now let's go towards the experimental evaluation. Again, the task is just to perform NLU, and under NLU, we have two steps: intent classification and entity extraction. What we do is we prepare database. This database is one of our clients' actual real world data, which is not open sourced. Then we perform the adaptation or fine tuning of that entire pipeline using this data. And finally, we compute accuracies of intent classification and entity extraction as a performance measure. And we also did comparative studies between sparse versus dense versus composite features. Data preparation is something like this. We have to categorize the data into our 4 intents, and within each sentence, within each customer query, if an entity is present, we have to tag that entity. So for example, car A in this example under product detail is tagged as a product, and where A is a variant of that particular car. So these are the 2 entities that we are tracking: product class and product name. We have around 120 examples for each of the complex intents and 50 examples for simpler intents, and a test case which is completely non-overlapping with the trained data. And we have same data prepared in English, Hindi, and Malayalam, and also introduced code switching so that the performance metrics across languages are comparable. And code switching we have introduced in 2 ways. One is transliterated Hindi, that is Hindi written in Roman alphabets together with English, and Hindi written in native script, that is Devanagari script, together with English. These are the 2 kind of code mixing that we have included in our experiment. Let's quickly move on to the entity extraction. So what we observed was, one obvious thing is that unrestricted entities had generally lesser accuracies than restricted entities, purely because of the nature of it. Then unrestricted entities, because their context is fairly similar, sparse features provided better performance. On the other hand, for restricted entities like product class and product name, which kind of appears mostly in that complex intents, right? Dense features provided better accuracies. And when we combine both of them, composite features are indeed being able to tap into advantages of sparse and dense featureizers and provided better accuracies than either sparse or dense features. And another important interesting observation that we made here is for code mixing, sparse features are considerably poorer than dense features, which is also sort of explanatory because the context of or the probability distribution of words that these sparse features are trying to capture is completely haywire in a code mix settings because 2 languages are interacting with each other. And we did intent classification. Again here, simpler intents, greet and goodbye, sparse features performed better. For complex intents, purely because of the sentence structure and the way in which users are, customers are expressing themselves, dense features performed better. This is also sort of expected because dense features are obtained from massively multilingual models, which learned each of these languages from inter-language data and intra-language data. So this is sort of expected. Again, code mixing, dense features performed much better than sparse features. And in both of our experiments, these composite features were actually better than either sparse or dense. Then we created one more experiment, which is very interesting in the sense that language specific versus language agnostic. Usually in any use case or application, language specific models are much better performing than language agnostic models. But in our case, we kind of had a different results, which is understandable or can be explained by the nature of the data. So the language specific models or even the massively multilingual pre-trained models are trained on very formal data like Wikipedia data or read books data. Okay, On the other hand, real world scenarios usually have to deal with conversational data, very informal kind of expressions that a user or a customer is using. In that case, actually, massively multilingual models, after fine-tuning, raise up to the occasion, and it was actually able to kind of capture these smaller, finer details and nuances of the real-world data, as opposed to language-specific models, which are trained on formal data and did not undergo any fine-tuning in this case. So that's towards the end of my talk. I'll just conclude now. Through this work, what we try to do is we develop a language agnostic pipeline for natural language understanding. And specifically, we used a conversational assistant as a study case to perform intent classification and entity extraction from short text messages, which are basically customer queries received by this conversational assistant. We provide rigorous experimentation. We performed rigorous experimentation with various featureizers and come up with a composite featureization, which is sort of able to tap into the supplementary/complementary nature of sparse and dense featureizer together to provide a truly language agnostic pipeline, having this composite featureizer at its core, at its heart. And it is able to deliver NLU performance, which is better than its language-specific counterpart. This observation is very relevant in real-world, real-case scenarios where users, like human beings, are not going to constrain ourselves to use a specific vocabulary using which a model is trained on, or use a specific conversational style using which the model is trained on. And it always makes sense to actually port the AI to come to the human nature rather than port the human nature to go to the level down to the AI. So yeah, that's our contribution here. Thank you for the patient attention.